All right, welcome everyone to 1.7. This is the precise definition of the limit. Now we already have a good intuitive idea about these limits. Back from 1.5 and 1.6, we can calculate out limits. But now we're going to kind of dive into the technicalities of these limits and get very precise. So in order to do this, the claim is we're going to have a lot of absolute value statements. Absolute value equalities, inequalities are going to be everywhere. And so in order to get us prepared for that, I find that it's a good idea to do a little bit of algebra review just to get those juices flowing again about how do we manipulate these absolute value inequalities and equalities. So we're just going to review a little bit of algebra stuff here about absolute values. So the first example that I have for us is that I would like to guess and check the solution to this absolute value equality. So go ahead and pause the video, take 2 minutes, try to get me the answers for this thing. Okay, let me go ahead and solve this for us. The first one, after staring at this for a little bit, I find that most people come across the answer x equals 6 should work out, right? Because if I take the absolute value of 6 minus 1, that's going to be the absolute value of 5, and that just gives us 5. So indeed, this works out, right? X equals 6 is a solution to this absolute value equality, right? Equation. All right, next up, this one's a little more difficult. Takes a little bit of thought, but x equaling -4 will also work. So if I plug in -4 everywhere I see an x, I get -4 minus 1. That's going to be the absolute value of -5, and the absolute value of -5 is +5. So there we go. These are two solutions, and in fact they are the only two solutions to this absolute value equation. Okay. Why do we care? Well, the claim is that actually absolute values help us express distance statements. So distance statements into something that we can actually manipulate, right? These mathematical equations. So for instance, in the above example, the claim that I have for you guys is that these solutions are the x values that were distance 5 from 1. Okay, don't believe me? Good, right? Let's go ahead and draw out our number line here. And so, let's see, distance 5 from the value 1. So I'm going to be interested in the value 1. And if I move 5 units to the right, right? 1, 2, 3, 4, 5. So I move 5 units to the right. Let's see, that would be 2, 3, 4, 5, 6. And that was one of our solutions, right? So when I move 5 to the right, I get 6. 6 was one of our solutions. Okay. What about in the other direction, right? If I move 5 units to the left, 1, 2, 3, 4, 5. So that would be 0, -1, -2, -3, -4. That was our other solution. So actually, these absolute value equations are telling us something about distance. That the solutions to this equation right here are all of the points that are distance 5 away from the value 1. Now, I would like to generalize this, right? So that it's not just for this specific problem, but we can actually use it for all sorts of problems. So the general statement says that the absolute value of x minus a equaling d, these will be all of the x values that are distance d away from the value a. So now we can use these kind of distance statements to solve lots of absolute value equations. All right, and it turns out actually in limit problems that we really want to be able to solve absolute value inequalities. So we've already done equalities or equations, right? Now let's talk about absolute value inequalities. For this problem right here, notice we've already solved something close to this, with the absolute value of x minus 1 is equal to 5. And the claim is this had some distance statement related to it. The claim is these inequalities also say something about distance. Let me go ahead and draw out again the solution that we came up with. So here's the value 1, and we said that these solutions were distance 5 away from 1. So up here was 6, down here was -4. So these are the things that are distance 5 away from 1. Notice we don't want it to be equal to distance 5 away from 1. We want it to be less than distance 5 away from 1. So as you could expect, if you went all the way to -6, this wouldn't work out, because 6 is equal to distance 5 away from 1. Likewise, if you went all the way down to -4, this wouldn't work out. But the claim is everything in between is less than distance 5 away from 1. And so you may recognize these from your favorite algebra class, right? Being able to sketch a solution to this inequality. So if it's any real number greater than -4, less than 6, the claim is it should solve this inequality. And notice that we got this by thinking about kind of the corresponding equation. So let's go ahead and verify this. So I'm going to choose maybe the value 2. The claim is 2 should be a solution to this inequality. Let's check. So the absolute value of 2 minus 1 is less than 5. Is that true? Question mark. Well, this 2 minus 1 is going to be 1. Take the absolute value. That's going to be 1. Is less than 5? Yes, absolutely. This is true. So 2 works out. Let's try another one. Let's try -3. There's -3. Let's plug this into my inequality. So I get -3 minus 1 inside of my absolute values. Is this less than 5? Question mark. Well, that's going to be -3 minus 1. That's going to be -4, but it's inside of an absolute value. So the absolute value of -4 is 4. Is 4 less than 5? Absolutely. So this one works out. Now let's take one that shouldn't work, right? So theoretically, for instance, like 7 out here. Probably shouldn't work. Let's check. So let's plug in 7. So I get the absolute value of 7 minus 1. Is this less than 5? Question mark. So that's going to be 6 is less than 5. No, this does not work out. 7 is not in the solution set. So it looks like we actually have a good result, right? Seems like everything between -4 and 6 satisfies this inequality. I'm going to go ahead and write my final answer in interval notation. So this is going to be all the way up to -4, not including it, going up to 6, but not including it. So we use these parentheses in our good old interval notation. So notice these absolute value inequalities also have kind of these related distance statements. So in this problem, the solution above are the values of x that are less than distance 5 away from 1. Okay, the claim is some absolute value inequalities like this, it's pretty easy to come up with a distance statement for these things. However, there are some out there that it's kind of complicated. So it's nice to have this following theorem. And this following theorem is going to help us, well, first of all, it's a little bit more algebraic. It's a little bit more mechanical, right? It's not as geometric and, about the distance and all this stuff, but it's still a really nice theorem. So, okay, if we have some nice d value, think of it like a distance greater than 0, then the absolute value inequality, and this is going to be the absolute value of some expression a, right? So it's going to have probably going to have x's in it, all that stuff. You can be as complicated as you want. Okay, the absolute value of some expression a less than d is the same as -d is less than the expression a is less than d. So this gives us a way to take these absolute value inequalities and rewrite them as compound inequalities. And the claim is compound inequalities are a little bit easier to deal with. So let's go ahead and use this theorem to solve the following example. The absolute value of 3x minus 5 is less than 4. So in this case, again, my a value is this expression. It has x's in it, right? And here is my d value. D is 4. So this is the same as -4 is less than a. There's my expression, 3x minus 5, is less than d, which is 4. Okay, and like I said, compound inequalities are a little bit easier to deal with. So I can go ahead and add 5 on all sides. And I can divide by 3 on all sides. And so we can see that the solution to this absolute value inequality is going to be x should be larger than 1/3, but smaller than 3. And again, we could go ahead and graph it out on a number line. So here's 3, and here's 1/3, for instance, and it would be all of the x values in between here. And we could also write it in interval notation. So all the way down to 1/3, but not including it, and then all the way up to 3, but not including it. So in this class, we're going to submit our answers in this interval notation here. Okay, notice if you wanted to think about this in terms of distance, it would be kind of difficult, right? Because we have 3x minus 5. The absolute value of this is less than 4. Our distance statement only really works when you have 1x minus some a value. So because we have 3x instead of 1x, the claim is, well, it's a little harder to apply this distance statement sort of stuff to this type of problem. So that's why this theorem is useful. Okay, so we've been dealing with just one absolute value inequality at a time so far. The claim is, in this section, we are really going to be able to need to juggle two absolute value inequalities. So here is a problem that has two absolute value inequalities, and this one takes a little bit to work out. It's kind of confusing, but the claim is this is where we need to get to in order to solve a lot of our limit problems. So in this case, we want to find some d value so that, and notice this has a nice distance statement to it. So if x is within distance d from the value 3, then, well, this one doesn't have a nice distance statement. So, right, it solves this, it is a solution to this absolute value inequality. So let me go ahead and write out some number lines here just so we can kind of visualize this. So the first one, we're centered around 3, right? So this is a distance d away from 3. So I want to know how much can I move to the left and to the right and still satisfy this inequality here, right? So what d can I move to the left and the right and still satisfy this inequality? So this inequality, right, the claim is it doesn't have a great distance statement, but we can still figure out what the solution to this is using this nice theorem that we have up here. So let's go ahead and break this apart. I'm going to write negative 4 is less than 2x minus 5 is less than positive 4 using that theorem. Now I'll add 5 to all sides, so I get 1 is less than 2x is less than 9. And now I'll divide by 2 on all sides. So I get 0.5, or a half, is less than x, and that's less than, well, 9 halves, which is the same thing as 4.5. And I guess remember, at some point we have to remember, right, that with these inequalities, you have to be kind of constantly paranoid that something that you're doing should make these inequalities flip, right? Sometimes inequalities flip on us. But the claim is, so far, nothing we've done would make these inequalities flip, right? So when you add or subtract values, they don't flip. And when you multiply or divide by a positive number, like positive 2, right, they don't flip. It's only when you multiply or divide by a negative number, that's when these things are going to flip. So far, we haven't needed to flip any inequalities, but that's something we should kind of have in the back of our mind. We should be worried about is that if you multiplied or divided by a negative number, these things should actually flip. Okay. So let's go ahead and sketch our solution here, right? We want x to be between x to be between 0.5 and 4.5. So here is 3, and let's take steps of a half. So that would be 4 right there, and then 4.5. And let's go down. So here would be 2, 1, and 0.5. So I would like to be in this region right here, right? So I want to choose some d value that I move away from 3, but that satisfies this inequality, aka stays in this region, right? This is the region where 2x minus 5 is less than 4. Okay, so let's go ahead and check. If I moved 0.5 away in either direction, would I stay in this region, right? So 0.5 away from 3. Yes, so d equaling 0.5 is a good d value, right? I would stay in this region. Likewise, if I move distance 1 away from 3 in either direction, I would stay in this, I would still satisfy this inequality. So d equaling 1 would also work. Now, how about 1.5? D equaling 1.5. Well, you have to be a little bit worried, right? To the left, you're okay, but to the right, you'd be hitting this open dot right here. But luckily, this is saying that, remember, that we're less than d, distance d, away from 3. So actually, d equaling 1.5 would also work. All of these would work. If I go one more step, though, if I do distance 2 away, notice to the left, I'm okay, but to the right, I've gone too far, right? So let me go ahead and do this one in red. So this is now out of this region, right? If I was to try to plug in, right, so distance 2 away, this would be 5 up here. If I was to try to plug in 5 here, well, that would go 2 times 5 would be 10, minus 5 would be 5. The absolute value of 5 is less than 4? No, it is not, right? So as soon as I go distance 2, now I'm going too far, right? Now I'm at the point where I could go up to 5, and that is not in this solution set, right? It does not satisfy this inequality. So d equal 2 does not work. However, any of these would be fine choices for d, right? Remember our question up here, it says find a d value. Well, here's 3 different d values. All of them work, and in fact, kind of anything between these would work as well. Like, for instance, 0.2 or 1.3, or right? So any of these d values would work, and there are lots of answers, but here are some of them, right? Okay, that is the end of this first video, a nice little bit of algebraic review. Like I said, this one's kind of complicated, and you're like, why would we even care about this problem? But it turns out this is going to become very applicable to our precise definition of limit problems. All right, so stay tuned. I'll see you guys next video.